Hello everyone, welcome to COMP251 Data Structure and Algorithms. In this video we are going to talk about the linked list. In the previous lecture video we have seen how to implement abstract data type list using an array. There were some advantages and there are some always pros and cons. So using the array-based implementation, using an array as the main data structure, it allows us to access to the indexes very quickly, and it is important for us in list because we want to have access to all the possible indexes in the list. And it was also good because the amount of space that you would take using your implementation using an array is exactly what you need for each item. You would store it in one cell of an array. And in addition to that array, the main data structure, you only need one more variable of type integer that keeps track of the number of items in the list. These are actually the advantages of implementing using array, and the disadvantages was that when we were actually inserting an item or removing an item at some arbitrary position, we need to shift the items to the left or right to make some space. And except that, actually the size of the array is fixed, right? So whenever the array is going to be full, that it can actually happen at any time, you need to resize the array. You need to get a bigger array and copy all the elements inside that array. So these are the disadvantages that we try to see is it possible to have to use a different data structure to implement this abstract data type list, so that we can actually get rid of the disadvantages. And yes, there is another data structure that we can use instead of array, which is called linked list. And we will see that the size of a linked list basically can grow as you store more items. And at the beginning, if you just have, for example, 2 items, it will just take some space, proportional to the number of items that you store. If it becomes 10 million, it just grows gradually and it takes as much space as it needs, and it grows. And it doesn't have actually that notion of shifting the items. We will see that if you are inserting an item at the beginning of the list, unlike the array that you need to shift all the items to the right to make a space at the beginning of the array, in the linked list we don't need to shift the items at all. But there are some actually disadvantages for the linked list as well that we will see them. So for example, accessing to a specific index in a linked list, you have to traverse through the whole linked list to find that specific index. And these are the disadvantages. And it also actually makes, in general, takes more space for, if you are, for example, creating 100 items, it takes some spaces to keep all of the references. So I'm not going to go in more details here. Just let me show you what is a linked list first, because I would guess that some of you probably haven't heard about the linked list before. So what is a linked list? A linked list is going to be a dynamic data structure that has been created from a set of nodes that has been linked together. So basically it's just like a chain. It is not an array anymore. Okay, so it would be, graphically, visually, if I wanted to show it to you, it would be something like this, that you have a node that, something like this, that you keep a value like 6 inside that, and you have another node that you keep another item inside that, for example 2, and this node is connected to the other node. Basically from the node 6 you know that where is the next item. From 2 you know where is the next item, which is going to be 7. From 7 you know where is the next item, which is going to be 8, and so on. So this is going to be a linked list, but when you create an abstract data type list using a linked list, this chain that you will see will be representing a list like this one, that for example 6 is going to be the first one, because as you can see I'm actually pointing at 6 as the head. This is going to be the beginning of your list, the head of a linked list. 6, then 2, then 7, and then 8. So basically a linked list just show you that instead of storing the items, all of the items that you put in your list in an array, that you know that an array in the memory is just like a sequence of cells that they are adjacent to each other. You will when you are actually creating an array and you are taking a space from the you're asking for a space, a part of the memory is given to you, and it will be actually divided to some cells, different indexes, and all of those are going to be adjacent to each other. But in a linked list, each of the items can be stored in a completely different in terms of the distance. They can be far from each other. The item 6 can be stored in somewhere in the memory. 2 has been stored in a couple of actual indexes, address of the memory, some other part of the memory, 7 some other. So the way that they are connected to each other, and you know that for example after 6 is going to be 2, is using a reference that we call it a link. So that's why this is called a linked list. Basically all the items has been linked to each other in a sequential way, in a linear way. From 6 you have access to 2, from 2 you have access to 7, from 7 you have access to 8, and always the last one, it's just like it's not connected to anything, and the connection there will be set to null to show that this is going to be the end of the list. So let me actually show you how we are going to implement a linked list. So when you are creating a linked list, you need a structure, you need a class for the node that has 2 main parts. One part of it is going to be the data that you store inside the node, and the other part is going to be a reference that is going to refer to the next node in the linked list. Okay, so when you are implementing this, you are going to have a class as simple as this. Again, here I am actually writing the type of item to be of type integer to make it simple. I'm not going to actually just make you confused with the generic implementation if you're not you haven't used that before. So at the beginning, let's just assume that the items that we are storing inside the nodes are going to be integer. Later on, in the full implementation, we will implement it in a generic way, of course. But so far, just let's assume it is going to be of type integer. So I have 2 parts. One part of it is going to be the item, the data that you are going to store, right? Let's call it item. The other part, we usually call it next. It's going to be a reference to the next node. And so what is the type of next? The type of next is going to be a reference which is exactly the same name of the class that I gave to this. So this is going to be a list name. So this is also you are saying that next is going to be reference to this class, reference to an object of this class. So when you are creating for example, a reference L1 of list node, you are not creating a node actually, right? Just like any other class, when I am actually, writing a list node L1, I am just declaring L1 to be a reference to list node, but I'm not really taking a space. If you wanted to take a space, you have to get the space for that. You have to use the operator new and create an object for L1. Okay, so now I have one node that the reference to that is L1. So L1 is one node, one object of list node. If I'm going to create a list, basically I need, if I'm going to, for example, create a list of 3 nodes, I need to have 3 objects of list node, right? For example, look at this. I am here creating 3 different nodes. I'm calling them L1, L2, and L3, right? So far, I'm just trying to show you what is the data structure of the linked list, which is going to be the main data structure for us in our linked list based implementation. So now I have 3 objects, L1, L2, and L3. Still, I don't have a linked list because they are not connected to each other. So if I want to create a linked list, I have to connect these items together to each other. So from L1, I wanted actually L1 to be the first item, and then I want L2 to be the second item, and then I want L3 to be the last item. So I need to preserve all of this connection. First of all, I'm putting some items inside them. Okay, this is not really actually some coding. I'm going to show you the concept of a linked list. Then L1 is connected to L2. To do this connection, I will set L1.next to be equal to L2. Now from L1 you have access to L2. So this connection has been preserved. Then I will connect L2 to L3. So L2.next will set to L3. Can you tell me that what would happen to L3.next? Remember, I said that always the last item in the linked list, the reference next is supposed to set to null, because it is when it is basically, an identifier to tell us that this is the end of the list. There is nothing more after this node. So we should always set the last or the reference next in the last item, set it to null. Either we can actually show it using this notation, which is from the physics, or you can simply just write down null inside that. Okay, here I'm just trying to grow the implementation here, and here is showing you, for example, you can write down different constructor for the list node. Here I have writing 2 constructors. This one is calling the other actually constructor, so that if you don't pass any reference, it is basically just create a node and set the next directly to null. Okay, look at this one. Okay, now I have, using this line, I have created a linked list with 3 nodes. Although I'm sure that you already actually noticed that this is not a sustainable way to create linked list. I'm just trying to show you different properties of a linked list and different operations that we define over the linked list. Then we will go to the implementation of or abstract data type list using a linked list. So most of the works that we do over a linked list will actually involve traversing the linked list, because here in the linked list, you don't have an array and indexing and that accessing to the indexes in an array, right? So whatever you are going to do with your list, for example, you wanted to print the list, you wanted to search for a specific item in the list, you wanted to reach to, for example, the third item, the fifth item, the 10th item in the list, some specific actually item in the list, you have to traverse over the items, right? You have to, for example, using this line that I'm actually writing here, I have created a linked list with 3 nodes, and you can see that I don't have access to this item or this item anymore. Or if you have a linked list with more nodes, basically we always only keep the access, the reference to the first item, because by accessing to the first item you can actually access to all other items as well. Not only that, I cannot keep actually all of the references. For example, if you have 10 million items in your linked list, if you have, I don't know, 1,000 items in your linked list, if you wanted to keep all of the indexes of the items, where are you going to store them? You cannot store them in separate variables, right? And if you are going to store them in an array, this is not going to be, a sustainable way. So if you're using an array, you just use an array. Why are you using a linked list at all? So you have a linked list, you only have access to the first item, and I'm going to show you the pattern that in most of the cases that we are working in a linked list we follow. We need to traverse over the linked list. So to traverse over the linked list, what I need is basically just another reference. Be careful, I am creating a separate reference, because if I lose the reference to the first item, the whole linked list is gone. Okay, so I will create some temporary variable. This is going to be a reference to the same class, a reference to list node. I will initialize it with L1, which is going to be the first item in the list, right? And if you wanted to traverse over the list, you wanted to visit all the items, what you should do is that just update P1 and go forward. How in the next step, what P1 is supposed to actually be referring to? P1 is supposed to actually refer to this item, the second item. But where is that? P1 is going to be referring to actually this index. So I can just update P1 to be P1.next. Okay, so this is the thing that I need to know. I can use a while loop and basically go forward over the list until P reaches to null. Whenever you see that I will actually keep updating P to go to P.next. So first it was actually referring to L1, then it referred to L2, it referred to the next item, the second item, then it referred to this item. And now you can see that whenever P reaches to null, in the last step, when you set P to P.next, P will be set to null, right? Which tells you that, okay, I reached to the end of the list and I'm done. How many times you actually will need to update P go to the P.next? It will be depending on how many elements you have in the linked list, right? We don't know how many elements, but we don't care. We can just write down, if you wanted to traverse over a linked list, you can start writing something like this, that P equal to, for example, L1, whatever is going to be the first item, and then using a while loop until P is not equal to null, P equal to P.next. Okay, so basically this is the main pattern that I wanted to show you. Using this pattern, you are tracing over all the items in a linked list. For example, you wanted to print everything in the linked list. You can just, for example, add some print p dot item, right? And then update p to go to the p dot next or whatever. So this is, you know, a very important pattern that you need to know when you are working in a linked list. So basically now you have the idea that what is going to be a linked list. A linked list, now that you know what is a linked list, which is completely different than an array, we wanted to talk about this fact that how we can implement an abstract data type list using a linked list instead of an array as the main data structure. Here actually the idea is that when I'm actually implementing an abstract data type list, basically what I need is just a reference, which is going to be the reference to the beginning of the list. We call it head of a linked list. And if you want, you can also keep track of actually the number of items that you have in a list. And that's it. All the data fields that you need to create, to write down your class for the abstract data type list using a linked list is going to be just the head and the number of items. But be careful, in addition to this class, you also need to have another class that is going to be the class for node. Each of the nodes in your linked list are going to be of type from a class, right? So unlike the abstract data type array-based list that we have implemented using only one class, in the linked list based of that, we need two classes. One class is going to be the class for node. The other class is going to be the main class of the list. That inside that you have to actually store the head. So here I'm showing a part of actually the code. Again, the code is available on Blackboard. I decided to record this video on iPad because I found a couple of actually issues when I was recording on my laptop. I couldn't get the best quality of the sound. But anyway, you can actually while I'm actually explaining it here, open the source code and we will go through it during the class as well. There are two classes in your in the slist class, slist source code that I have posted on Blackboard. The first class is called slist node. Here, basically, slist is this S stands for singly linked list. That later on I will explain what does this mean against doubly linked list. Okay, so slist node is going to be the class for each node in our linked list. What are the items inside? What are the data types inside this class? Item and a reference to next. This code is going to be generic. Okay, so the type of item, I have written it as any type, and you can see that I'm following the same syntax that I'm mentioning the name of the any type there. And when you are writing the reference, be careful, you should also write down the actually any type in front of the reference everywhere that you are actually using that name of the class as a reference. So we have the rest of it is going to be similar to the previous example. You have two data types, item and the variable a reference to the next item. And I also need one class for slist, right? This is going to be the main class for us, slist. Again, you need to actually just use the same identifier, any type, exactly the same dictation. Be careful that you don't miss that. Inside the slist, the only two data field that I keep is going to be one reference, which is going to be the reference to the beginning, to the first node in the linked list, which I'm calling it head. And also I'm keeping track of the number of items as well. To be honest, you don't really need to keep track of the number of items, unlike in array implementation that you need to keep track of the number of items in the array-based implementation. Here you don't need to keep track of the size. But if you keep track of it, if you keep a variable for that, you just can write down many of the methods in more efficient way. So I'm just sacrificing one integer variable so that later on, for example, you want to know how many items you have in your linked list. Instead of always counting all of the nodes, you can just return this variable size. You should be just careful that whenever you are adding or removing an item, you maintain the variable size and you update it. Okay, so in the constructor of a singly linked list, what I need to do is I just need to create an empty list, right? So an empty list means that there is not even a single node. Head will be set to null and size will be 0. Okay, so this is the constructor. So now I'm going to show you a couple of the methods that we define for a linked list. Our linked list is empty at the beginning. Then, okay, we are going to add some item to the linked list, right? How we can add an item to a linked list, and we want to see how we can write the code for that. Let me first visually show you what would happen, and then we can write down the code for that. So at the beginning, if I create, a singly linked list, an empty singly linked list, something like this, X is going to be a list of type string, which is empty. So if I'm going to visualize it for you, this is going to be an object of list, head is null, and size is 0. This is not a node. Be careful. What I'm showing you here is this is not a node. This is an object of the list. And I'm just showing you that head is null, which means that there is no node, nothing, and the size of your list is going to be 0. It's just like if you execute this line, this object will be created. Then just assume that I wanted to, for example, add something to the beginning of the list. Basically, I'm trying to implement a method like add first, which the specification of this method is that if you call this method, the item that you are passing to the method will be added to the beginning of the list. So if the list is empty and you are adding something to the beginning of it, so something that would happen is that, for example, one node, because this is going to be a linked list, you should create a node and head should refer to that node. And the item inside that node should be set to, for example, milk. Okay, so after executing this line, what I would expect to happen is this, that one node will be created, the value inside the node will be set to the value that I'm passing here, and the head should supposed to actually refer to that node. Okay, and be careful here, the next in the node will be set to null as well, because this is the first item that you have inserted. Okay, what would happen if I, let me just clean here a little bit. What would happen if I call another add first? For example, or if I call x dot add first, another item, whatever you like soap. Okay, in that case, again, this is at first, right? You wanted to add the item at the beginning. So, and you don't want to lose this item as well. What you want to happen is that you wanted to have another node. The item inside that node should set to soap. Head should set to should refer to this node, this new node that you have created, and you shouldn't lose the previous node, the previous value of head, right? Head previously was referring to this node, and now it should refer to this one. But you should be careful that the next inside this new node should refer to the previous value, the previous value of head. Head was referring to this one, and this one should actually update it to that. So you got the idea that what needs to be done. In general, this is something like this, that whatever item that you have, it doesn't matter if it is 0 or, for example, 410, whatever. What you need to do is that you need to create a new item, new node. You need to make sure that this item, the next in this item, will refer to the previous beginning item, the previous head. And then you also need to update head to refer to this node. Okay, so it's just actually 2 steps. The first step is that you need to create a node, okay, and you pass the item that you wanted to store to that, and you also make sure that the reference in this node is going to be head. Okay, so I'm creating this new node, and then in the next step, what I need to do is that I just need to update head to refer to this one. This link has already been preserved here. Okay, just assume that you we have the constructor for this node that you pass the next, and next is going to be head. And the only other thing that you need to do is just updating the size, just maintaining the size. Make sure that because you are adding a new item, you have to increase the value of the size as well, right? So one thing that I'm going to show you here is that these 2 lines basically can be combined, and I can actually do it, write it down in this way, that create a node, set the next inside that to head, and just set that reference to head. I didn't do anything complicated. I just combine these 2 steps and get rid of this arbitrary this temporary variable here. I don't really need that. I can write it in just 1 line. So can you tell me that what is going to be the time complexity of adding a node at the beginning of a linked list, adding an item at the beginning of a linked list? It is clear that it doesn't matter how many items you have in your linked list. If it is just 1 item, if there is nothing, if there is 10 million node, when you are adding an item at the beginning of a linked list, it just takes these 2 lines to be executed. It doesn't depend on the number of items. So basically the time complexity in this case is going to be constant. Now you can actually compare it to the case of the array-based implementation. In the array-based implementation, if you are inserting some item, a new item at the beginning, you have to shift all of the previous items, right, to be able to make some space for the first actually you need to make the first index empty, right? Available. So you have to shift all the items to the right and make a space. So adding to the beginning of an array is going to take linear time, O of n, but adding to the beginning of a linked list is going to be done in constant time. So these are some of the advantages of a linked list, of course. Okay, let me show a couple of other methods that we can write. This method display is not really in your source code. You don't need a method like this. I'm just writing it to show you how we are traversing over the list. It is just a simple method that to write down over a linked list. So for example, you are printing all the items in your linked list. You can write down a method like display. So here you are traversing over the linked list, right? You wanted to visit all of the nodes. So this is that trick that I showed you. You need to define a reference and be careful. I cannot change head. Head is the beginning of a linked list, and if you lose it, the whole items in the linked list are gone. I mean, the whole linked list has been ruined. Okay, so when you are working with head, be careful. Don't touch it. If you are not going to actually add something to the list or remove something from the list, if you are not going to add something at the beginning of the list, or if you are not removing something from the beginning of the list. Okay, I need some temporary variable. I will call it current. It just stands for the current node. So current will set to null, and then using a while loop, this is exactly what I showed you before. You can just keep updating current to current.next until it reaches to null, and always just print the value of the item that has been stored in the reference current. Okay, so it actually, as it goes forward, it actually traverses over the whole items, and it will stop whenever it reaches to the last item and the current became null. Okay, another method that I'm going to discuss here is deleting from the beginning of the a linked list. We call it remove first. Okay, this is the code that I have written for the remove first. You can see that just like the way that we add an item to the beginning of the list, if you are removing an item from the beginning of the list, you just need to update the reference to the beginning of the list. You just need to update the head. So let me just show it to you using this actual picture, this example here. Assume you have a linked list. What you need to do is that you have to remove this item, right? So basically what is required to be done is head should refer to this item, the next node. Where is this next node? Where is the reference to this next node? You have access to it through this link, right? What we need to do is just updating. We don't really need to manually delete the node. The only thing that I need to do is just updating the head. If I update the head to head.next, I'm done. Head will refer to this node, and the garbage collector will remove this node later. I don't need to be just worried about that node. And the other thing that I need to do is just decreasing the size. Okay, now I have a question for you. What would happen if the list is empty? Does this code work properly in this case? You can see that I have already taken care of that case. I have added this if statement. It's just like a sanity check at the beginning. And I'm checking that if head is not equal to null, I will change head to head.next. Otherwise, if head is null, if the list is already empty, you cannot remove anything from that, right? So if head is null, if you don't do this sanity check here, you are going to get an error because head is null and head.next doesn't have any meaning. But using this if statement, I am avoiding that runtime error. And yes, the code works safely, and there is no error here. So the other question that I have for you here is that what is going to be the time complexity of removing an item from the beginning of a linked list? Here again, you can see that there is no loop. I am not going through all the items when I'm removing an item when I'm removing the first item from the linked list. I'm just updating the head and updating the size, that's it. So exactly like adding an item to the beginning of the list, removing an item from the list is going to be done in constant time, O of 1, which is completely unlike the linked list, the array, that you can see that if you are removing an item from the beginning of an array, so you have to shift all the items to the left, right? So in that case, that was O of n, removing an arbitrary item from the array-based list, from the beginning of the, removing the first item from the beginning of, the first item from the beginning. Anyway, that's just a duplicate. I'm duplicating all of these words. Removing the first item of the array base, this is going to be linear. Okay, so far we have seen inserting and removing from the beginning of a linked list. We are also interested to see what would happen if we remove an item from the end of a linked list. Okay, so if you are, for example, adding an item to the end of a linked list, what would happen? You need to actually create a node and change this reference to refer to this new node that you are going to create, right? And set this one to null. Okay, so basically what is needed to be updated is this reference. But do I have access to this reference? Which is basically going to access to this node. I don't have access to this node, right? Because I only have access to the beginning of the list. I need to actually use again traverse over the list using a temporary variable current and go forward until, be careful, here you would stop before current became null, right? You would stop whenever current.next is null. So in that way, you would actually understand that, okay, I should stop here. I need to create a node and change this reference to set to this one. Okay, so what I wrote as the code is going to be something like this. I have created a temporary variable current, set it to null, and until current.next became null, I will just update current to current.next, it just go forward, and whenever I reach to that point, I will create a new node, current.next will set to that new node here, okay? This link will be preserved, and the size will be increased. So I have a question for you. Is there any error if the list is empty? What would happen if the list is empty? Look at the code and tell me that what would happen. Although, of course, you are not here and you cannot actually talk to me here. If the list is empty, head will be null, right? So the first value of the current, the initial value of current will be null. So when you are checking current.next, you are basically calling next over null, which hasn't been defined. So this code is going to crash. I'm actually writing it first in this way to show you that you have to be careful when you are working with a linked list. You can easily get runtime error because of referring to something null, or you can easily lose track of the head and just ruin everything. So be careful when you are writing the code for the linked list. So you should consider this a special case. I can do this by adding a sanity check at the beginning, which is checking that if head is null, it is telling me that the list is empty. If head is null, the only thing that I need to do is that I just need to create a node, because the adding to the end of the list is just like updating the head, right? Because there is nothing in the list. So I can just do it with one line of code here. Okay. Otherwise, if head is not null, I can just do the rest of the code just like before. So I have actually solved that issue here. But can you tell me that what is going to be the time complexity of this code? The code is safe. It's definitely working. What is going to be the time complexity of the code? You already actually see that I have a loop and I need to go through all the items until I reach to the last item, right? So because of this, the time complexity definitely is going to be linear, because it needs to start from the head and go until it reaches to the last item. So adding to the end of a linked list using this implementation, the current implementation, is going to be linear. But what if I actually change something in my implementation? What if, in addition to keep track of the first node in the list, I also keep track of the last node in the list as well? We usually call it tail. It's just, in contrast to the head. Head is going to be the first item, the first node. Tail is going to be the last node. So be careful. By adding this new reference, not only now you have to take care of head, you also have to take care of tail as well. So in all of the previous methods that I showed you, all of them have been written for the case that you only have had head. But if you are going to add tail, you have to make sure that you maintain tail as well. But if you keep track of tail, what would happen here is that instead of traversing over all the items starting from the head until you reach to the last item, now I have access to the last item. That reference that needs to be changed, I have directly access to it. The only thing that I need to do is just creating a node, updating this reference to set to that, and then update tail to refer to this new node, which is actually basically these two lines. Tail.next will be set to this node, right? This link will be preserved, and then tail will set to tail.next. So tail will be actually set to this link, which is going to be this one. Now this is the new final node, the new last node. So instead of doing it in linear time, it is clear that it can be done in constant time. If I just, I sacrifice one more reference, but I got this method to be done in constant time, and that's great. You always wanted to actually decrease the time complexity if the, the sacrifice that you need to do is just a couple of variables. Be careful, just variable, not an array, for example, okay? Okay, but here I have a question for you. Everything is okay with this code? Are we checking all the special cases? What would happen if the list is empty? Does the code work properly? It is clear that if the list is empty, not only the code will crash, but also there is something more which is missing. Head also needs to be updated when the list is empty and you are adding something to the end of the list. So if the list is empty and you are adding something to the end of it, basically that item is going to be equal, both head and tail should refer to that item, right? And not only that, this tail.next will crash because tail is null and you cannot call the next over tail. Okay, so I have to again do a sanity check. I am checking that if tail is null, it doesn't matter if tail is null or head is null. Basically, whenever head is null, tail is also null. Whenever tail is null, whenever head is null, tail is also null. Whenever tail is null, head is also null. Both of them will be null. If it means that just the list is going to be empty. So in that case, you just set tail to this new node that you would create, and also set head to be equal to tail. Okay, otherwise, if it is not the case, the previous piece of code, those 2 lines are going to be enough. And just at the end, increase the size as well. Okay, so now the code is going to work, and it is clear that the time complexity is constant, either if it goes here or here, just the constant amount of work will be required. It doesn't matter how many items you have in the list. If it is 0, if it is 10 million, it is just constant number of statements that needs to be done. Okay, so we have already checked that adding an item to the end of a list can be implemented, end of a linked list can be implemented in constant time by preserving a reference as the tail, as the last item. So that's good. That's we can actually just keep track of the tail and make sure that adding an item to the end of the list can be done in constant time. What about removing an item from the end of the list? So far we have seen that adding and removing both from the beginning of the list can be done in constant time, and adding to the end of the linked list also can be done in constant time. What about removing an item, deleting an item from the end of the list? When you are deleting an item from the end of the list, a couple of things needs to be done, right? This reference needs to be set to null, right? And also tail needs to refer to this node, the node before tail. So we need to access to this node basically to be able to set this reference to null and also set tail to this one. But where can I find this node? From tail, you don't have access to it. You should start from head and go down until you find this node, which is going to be exactly before tail. So again, what I need to do is that I have to start from head, go forward until I reach to a node that I know this is going to be before the tail. Because of this, it is clear that removing an item from the end of a list, even by keeping track of the tail, cannot be done in constant amount of work. You need to traverse over the items starting from the head until you reach to this node, which is exactly before the tail. So the time complexity in this case is going to be linear, and we cannot actually make it better than linear if you have a singly linked list. Later on, I will actually at the end of this lecture, I will briefly talk about the double linked list, which will solve this issue, but this is not the main topic of the course. The main topic of the course is just the single linked list. So far we have talked about insertion and deletion at the beginning and at the end of the list, both extremes. What about actually inserting and removing from somewhere in between some specific indexes, right? For example, insert an item at index 10, remove an item at index 20, something like this. So it is clear that if you wanted to do any of these actually actions, you have to start from the head, count down until you reach to the specific index that you are looking for. And whenever you have reached to that index, for example, you are going to insert, this is going to be index like 9. Okay, so you need to find this reference. You start from the head, go down and count until you reach to, for example, the 9th item, basically the 10th item, because the indexes starts at 0. And then you wanted to, for example, insert at index 10. So after the index 9, you need to create a node. If you have access to this previous item, you can just update this index and also change this index, update this reference, and also set this reference to refer to the previous actually reference of this one. So these are the main actual actions that needs to be done in this case. The only thing is here is that you have to basically traverse over the array, over the linked list. So again, adding or inserting at arbitrary position, removing from the arbitrary position in a single linked list, both of them are going to take O of n. You can double check the source code. I didn't actually just copy the source codes here, but you can find it, all of the implementation. I think I have again erased some part of the implementation because they are going to be a part of the lab exercise that you will do for the next week. But except those 2 methods that I have erased, the rest of the implementation is complete. Just make sure that you read the implementation before our class. We are almost done. These are the main methods that we needed to cover, and I have actually implemented them in the source code as well for you. Some other actually methods, just take them as an exercise. For example, you can assume I wanted to add a method to the linked list, to the single linked list that we have, that you pass another single linked list and you concatenate the one that you have, the one that you get to, the main one that you have. So for example, you call L1 dot concat, for example, concatenate L2. So in this way, it's just like the whole linked list L2, all the nodes in L2 should be concatenated to L1. You can do it in different ways. For example, assume that when you are concatenating all the items in L2 to L1, you don't need to keep them in L2. You can just assume that L2 will be empty. Okay, so in that case, this is just, an exercise for you. I'm just trying to write down an exercise for you. You should be careful. There are plenty of special cases in this case. The main thing that you need to do in this case is that because I don't want to keep a copy of L2 separately, I can just, keep all of the items here, all of the nodes in L2, don't touch them at all. Basically, the only thing that you need to do is just updating this reference. This reference needs to be referred to this one, and then you need to update the L1.tail to refer to the last item in L2. So concatenating two linked lists basically can be done in constant amount of work, right? You don't care how many items you have in L1 or how many items you have in L2. This can simply be done in constant amount of time or work, just because you only need to update this reference and also update this reference. But in terms of the implementation, there can be many special cases. what would happen if L1 is empty? What would happen if L2 is empty? What would happen if both of them are empty? Okay, so be careful when you are writing the code for this linked list, because of all these references that you have to update. You are going to have a good chance that either missing some of the nodes or getting some null reference exception. So it's just the time complexity is going to be constant, right? Because you just need to update this connection here. Okay, so I'm done with the linked list. Basically, now you have already seen the advantages of using a linked list. If you are using a linked list, inserting at the beginning or deleting from the beginning is going to be done in constant amount of work. If you are inserting at the end of the list, also it can be done using in constant amount of work, unlike the linked list, unlike an array that if you are adding or removing from the beginning, both of them are going to be linear. And the other thing is that you would never require to copy all the items because of, for example, running out of space. As far as you have access to RAM, your linked list will grow dynamically, and you would never need to just duplicate the size of the array and that issue that you have with the fixed size array. But the disadvantages of the linked list, of course, there are some pros and some cons. So the disadvantages is that whenever you are going to access to the nth item, for example, in array, it can be done in constant amount of time because it's just accessing to that specific index in the array, unlike in the linked list that if you wanted to implement the method get index, you basically need to traverse over the whole linked list until you reach to that index. So it needs to be done in O of n, unlike in the linked list, which is going to be in constant time. The other actually disadvantage is that inside an array, you would for each item you would just actually store it in each cell of the array, right? But in a linked list, you have to not only take some space for the item, but also take some space for the references as well. All of the nodes are going to have one additional reference as well. So you are taking more space, of course, in that terms. This is just a summary of what we have discussed about the singular linked list and array. If you have a singular linked list, adding at the main three methods that I'm interested about is just adding or removing, accessing. This get is just like access to the first item, access to some arbitrary index, whatever. So these are the main methods that I care about, and that's why I actually just summarize these ones in terms of the time complexity. So accessing to the first item, adding to the first item, removing from the first item, all of them in the case of a single linked list can be done in constant time. Accessing to the last item can be done in constant because you have access to the tail, right? Adding to the last item at the end of the linked list can be done in constant again, but removing from the end of a linked list needs to be done in linear time because you don't have access to the item before the tail. So everything about the first and last, most of the things about the first and last index are good in the linked list, but the issue is that if you are accessing to the arbitrary index, this is linear. If you are removing from arbitrary index, it is linear. If you are adding from to the arbitrary index, it's linear. Removing to arbitrary index, it's linear. And this is the summary of the array. If you are adding or removing from the beginning of the array, it is going to be linear, which is constant in linked list, but accessing to arbitrary indexes can be done in constant, and removing from the end of the array, unlike the linked list, can be done in constant, right? Because if you are removing the last item, basically the only thing that you need to do is just updating this reference. The number of items will be decreased, and that's it. The number of items will be, for example, if it is k, it will be k minus 1. You don't need to shift if you are removing the last item. If you are adding to the end of the array, it can be done in constant, because you just need to put it here, right? You don't need to shift the items at the if you are adding them to the end of the array. Accessing to the items beginning and arbitrary, all of them can be done in constant, but again, adding or removing at arbitrary position in the array is going to be linear, because you have to shift the items to the right or to the left. So this was the case that you have a singly linked list with both references head and tail. If someone asks you about the case that you have a singly linked list and you only have access to head, so the time complexity will be different for some of the methods. Of course, accessing to the last item, removing from the end of the list, adding to the end of the list, all of them should be done in linear. So it's different than when you have access to the tail. When you have access to the tail, these two can be done in O of 1 or theta of 1. Okay, I am almost done with the single linked list. Let me briefly talk about the double linked list. That issue with, remember we had an issue with the single linked list that we had a lot of issues actually. But one of them was that when you are removing an item from the end of a list, we cannot do it in a constant amount of time, right? Double linked list will solve this issue and allows you to do removing from the end of a linked list in constant amount of time. And the whole idea of a double linked list is that in the single linked list, you only each item only have access to the next node in the linked list, right? So you have the head, and from the head you have access to each node will actually refer to the next node. In the doubly linked list, instead of only keeping the next item, each item has access to the next item and also has access to the previous item. Okay, so it's just like if you have this is showing you a double linked list with 3 nodes. This is going to be head, this is going to be tail, and each node has a reference which is called next and a reference which is called prev. So for the head, the previous is going to be null. For the tail, the next is going to be null. So by adding one more reference to all of the nodes, not only you can start from the head and go to the tail, you can also start from the tail and go forward. And because of that, when you are removing the last item, you need to access to this item, right? You have that reference. So removing the last item can be done in constant amount of work. Although this code is not complete, but I just wrote it to show you, to give you the idea. Assume you have these 3 items and you wanted to remove the last item. What needs to be done basically is that this reference, basically this node is supposed to be removed, right? So if this node is supposed to be removed, this node is going to be the new tail. This reference needs to be updated, right? And also this reference needs to be actually updating and refer to this one. So these two things needs to be changed. How we can do that? Let me actually show you. This tail.prev, okay, tail.prev, this is tail referring to this node. The previous is going to be this reference, and dot next inside that is going to be this reference. Okay, I need to set this one to null. So tail.prev.next will set to null, and then tail should be updated to what? Tail should be updated to tail.prev. Okay, so this is basically going to be tail should update it to tail.prev, which is this node, and you are done. Only these two statement needs to be executed. Of course, you have to take care of too many special cases. What would happen if the list is empty? What would happen if you only have one item? What would happen if you have only two items? So basically, not only you have to take care of what if the list is empty, what if the list has one item, what if the list has two items. All of these are going to be the special cases in the case of a double linked list. But that table of time complexity will be updated. This is the table for the singly linked list. This is going to be the table for the double linked list. Still accessing to arbitrary position, removing, adding to that, all of them are going to be linear, but adding or removing or accessing to the beginning or end of the double linked list, all of them can be done in constant amount of time. Of course, the Java application, Java collection API are going to have a data structure for doubly linked list as well. We don't have a single linked list in Java as far as I know. We just have a double linked list. This is basically called deck. Be careful because this is not only doubly linked list, it is actually implementing a specific data structure. So don't be confused with the first assignment of the course, because in the first assignment of the course I'm going to ask you to implement an abstract data type that I'm calling it deck, but that's different than this one. Okay. All of these methods that actually most of the methods that we have discussed for the single linked list, they have been defined for the double linked list in the deck in the Java collection API as well. Add first, add last, add, get, index of, remove first, remove last, and many more methods. Because of course this is going to implement list, deck is also a list, right? Deck is an implementation of the abstract data type list. List is an interface in Java, and deck is also implementing that. So this is the first example that I showed you using the array list. I kept the whole example the same. I just changed the first line of it and change it to instead of use array list, now I'm creating an object of a linked list. And you can see that because they are just following the same interface, all of the methods, the name of the methods are going to be the same. I can just keep the full example the same, but of course the object that I'm working on is just a different implementation of that abstract data type, the abstract data type list. This time I'm creating an object of a linked list. here it's just showing you this nice thing about having a fixed name of all the methods, make it fixed, and you can have different implementation, and when you are using it, maintaining the codes are going to be very easy. So I'm done with this lecture. Please read the source codes. If you had any question, come to the office hours, or we can talk about it during our class.